Hello, everybody. Welcome to CERN. Welcome to the CCC, the CERN Control Centre, the place from which the CERN accelerator chain is managed. My name is Piotr, and this is Chetna, and today we're going to be talking about the heavy ion run that just ended. So, the beginning of this week, I think 4 a.m. on Monday, one of the operators here in the room pushed a button that dumped the heavy ion beam after 5 weeks of having heavy ion collisions in the Large Hadron Collider. So our guests today are going to be experts from the CCC to talk about the heavy ion side of things, the accelerator side of things. We're going to have experts from the 4 big LHC experiments to talk about the physics. And also we're going to talk about practical applications of heavy ion beams. So we're going to have an expert from the HARTS project. What's that? Stay tuned to find out. And then at the end, we're going to have a question and answer session with questions from you, the audience, that we're going to answer here. Everybody, all the experts are going to answer your questions. But first, let's go back to before the heavy ion run started. Chetna, you took a tour of the experiment control rooms and the CCC as they were just preparing for the heavy ion run. So how was the atmosphere like?
Yeah, I was there right before the collisions at the CCC, and I also took a tour of control rooms in each experiment. And for example, I remember one thing I can tell you, there was a lot of food on the tables of the control rooms, which tells me that I think students, technicians, physicists have been preparing for this for months and years, and they have day shifts, night shifts. So lots of food, lots of coffee, a lot of anticipation. And when the beam collisions happened, it was a really exciting moment from each control room. So let's take a look how it was.
This is a very exciting period now in the CCC because we're getting the machine ready to start injecting ions, lead ions, instead of the usual protons that we have in the LHC. This will be the longest run for lead ions in the LHC, and it's also the first one after 5 years.
Once per year we collide for 1 month heavy ions at the LHC, and they offer the unique possibility to create a new state of matter, the so-called quark-gluon plasma, in which quarks and gluons, which are usually bound into baryons and mesons, so confined states of matter, that they roam freely and create this quark-gluon plasma, and we try to study its properties.
What I found surprised in the last round of data is that not only in the lead-lead collisions, but in the proton-proton, proton-lead collisions, we also see some signal of the quark-gluon plasma. So in this data, we would like to know in what kind of conditions that the quark-gluon plasma will emerge, and also what is the smallest droplet of the quark-gluon plasma.
We are going to have a larger data set and also higher collision energy. We hope that we'll be able to understand better this fundamental strong force and also understand more details about this quark-gluon plasma. But also we are actually really excited to study more collisions of photons, because we can actually use the LHC as the photon-photon collider.
LHCb has the unique opportunity to inject gases into the LHC accelerator. This year will be argon, and we can collect simultaneously at the same time lead-lead or proton-proton and proton or lead gas collisions. So this year we will be able to study lead-lead and lead-argon at the same time.
Ready to go? Yes.
All right, welcome back to the CCC, CERN Control Centre, where everyone works 24/7 to run the massive CERN accelerator complex that you just see behind me. So today we have 2 very special guests from the CCC, Roderick Bruce, who is an accelerator physicist from Sweden, and Matteo Solferoli, who is an LHC engineer and has been part of the LHC operation since 2009. So today, if you have any questions on lead ions, Roderick is your person. And if you want to know anything about the Large Hadron Collider machine, ask Matteo. So, hi Matteo, hi Roderick.
Hi Chetna.
So usually the Large Hadron Collider is known to collide protons, right? So Roderick, what was special about this heavy ion run? What did you collide this time?
Right, so indeed we collide protons, typically most of the time. But about 1 month per year we typically collide ions. And what we're talking about is fully stripped lead ions. So this means that we take lead atoms, so it's a nucleus with 82 electrons around it, and we strip off all the electrons, so we have only the nucleus left, and the nuclei is then what we collide in the LHC.
Is that why you call lead ions heavy ions?
Indeed. So lead is one of the heavier elements. It consists of 208 nucleons. So one lead ion has roughly the same mass as 208 protons.
Okay. And Matteo, I'm curious to know, where do the lead ions come from in the CERN accelerator complex, and how do you accelerate them?
Yes, indeed, as Roderick just explained, the ions are bigger and heavier than the protons, so they cannot follow the same path in the acceleration in the CERN accelerator complex. So they start from a linear accelerator, which is called LINAC 3, instead of the LINAC 4 that is used for the protons, and they are then injected into the low energy ion ring, which is a special machine dedicated to the ions, from which they are extracted into the proton synchrotron, the PS. At this point, in fact, they catch up the same path as the protons, and from the PS they are extracted the 26 GeV proton equivalent energy into the super proton synchrotron, which is the SPS. And from this, they are extracted 450 GeV into the LHC. Once they are into the LHC, they're accelerated to a maximum energy, which is a collision energy of 6.8 tera-electron volt per charge. This is an unprecedented energy because in the last run in 2018, they were accelerated to 6.37 tera-electron volt per charge. So this was a special run this year.
I'm always fascinated to know how everything's connected, and there are so many more accelerators beyond the Large Hadron Collider. So I was wondering, Roderick and Matteo, what were some challenges you had to overcome during this run?
Right, there are actually we have quite a few challenges with the lead ions. There are many beam physics processes in the LHC which are special only for ions. So one of them is that when you collide two fully stripped lead ions, there's a process where one of them can pick up an extra electron. So out of the collision point comes a beam of one electron ion with a nucleus and just one electron. And then this particle has the wrong charge, so it follows the wrong trajectory. It is wrongly bent by all the magnets. And then it hits one magnet where it causes heating. So this magnet can then lose the superconducting state. And to handle this, we have installed something called collimators, which are new for this run to protect this magnet.
So another important challenge that we embraced this year is the so-called slip stacking. This is a very complex process that we do in the SPS. This is an RF gymnastic, a radio frequency system gymnastic, on which we take two groups, we call batches, of 4 bunches, which are spaced by 100 nanoseconds, and we overimpose them, interleaving the bunches. So what the result of this is a batch of 8 bunches spaced by 50 nanoseconds, so closer to each other than the original beam. And this allows us to inject more particles into the LHC. So in the end, the real gain is that we are able to create more collision per unit of time into the LHC.
Hey, I like that analogy with gymnastics. So thank you, Matteo and Roderick. Now it's time to move on to the hero of the show. No, I don't mean my co-host Piotr. I mean the ALICE experiment, who has been waiting for this heavy ion data since 5 years. Let's take a look.
So ALICE is the experiment dedicated to studying quark-gluon plasma in heavy ion collisions. So our expert today is Sarah Porteboeuf, the run coordinator of ALICE experiment. Hi, Sarah.
Hi.
So maybe before we launch into all these experiment stories, let's just, to set the stage, what is quark-gluon plasma in the first place? The thing that you all study.
Yes, so I guess you all have a knowledge of phase transition. What are the phase transition? It's when you take simple water, you put it in your in your freezer, and then you get ice, and then something that was liquid becomes solid. This is a phase transition of ordinary matter. And here what we do is that we study the phase transition of nuclear matter. So nucleus of atoms are made of protons and neutrons. All this is extremely well structured with a strong force, and you have inside quarks and gluons. And nuclear matter is in a state for which we see the standard matter everywhere. But what is really nice is that, as for water, if you change the quantities, like the pressure or the temperature, you can change its state. And what you will have is that strong force has a very interesting properties, is that if you increase the energy or you compress, then the quarks and the gluons, which are really strongly bind into the protons and neutrons, they become free inside a matter that we call the quark-gluon plasma. So it's called a plasma as an analogy to electric plasma, because we believe that quarks and gluons are free. And this is a very interesting state of matter that have existed in the very first millisecond after the Big Bang. And this is exactly what we study here at LHC with ion collisions.
So going back to the Big Bang.
Yes.
Basically. So how did it go this time around? Because you were waiting 5 years for these heavy ion collisions. So why was this run special in any way for you, for Alice?
It was super special because we got we already studied quark-gluon plasma in the first 10 years of LHC, but then so there's a lot of things that we understood and a lot of questions that were still open. As always in research, you find one answer and 10 more questions. And this is why we designed new upgrades to be able to collect more data and to be able to do much more precise measurement to answer all these new questions that are arised. And for this, we changed all our electronic readout to be able to change our data taking from trigger mode, where we were only collecting data based on some input signal. Now we collect everything, so all the data that we receive in ALICE.
So how much is that?
So then this allows us to go from 8 kilohertz data taking, which is to 50 kilohertz data taking. So it means 50,000 collisions.
50,000 collisions per second?
Yes, 50, yes.
And you're storing all of that?
And we are, so no, because this you cannot. So what we have is that the bandwidth of raw data that we collect is enormous. It's 1 terabyte per second of raw data. Mm-hmm. And if you store that, it will be very, very expensive. So what we do is that we design a model to be able to reconstruct the data online, to put them in shape. And so what we have at the end of this online compression is something which is closer to 40 gigabyte of 100 gigabyte of data, which is already something really huge.
And so did it work? How did this run go with this? Because this is the first time you've used this new system?
Exactly. It's the first time we were able to take data within run 3 with a complete new setup. From our perspective in ALICE, it went super well. We were extremely happy with this tremendous data sample because we were able to collect 50 more time statistics that we had in run 2. So this is a huge data sample that we will have now to analyze during the winter.
50 times more data compared to what you've have.
Yes.
So when can we expect some fantastic new results?
So just before, so I was a bit late arriving here because we were having a meeting with all the coordination to prepare the program for the winter for people to analyze this data, to first of all to finalize to do the calibration of the detector, which is extremely important to extract physics results. Then also to do to finalize the reconstruction, because what we do online is compression, but then you need to reconstruct everything with proper calibration, and then to do all the physics analysis and extract all the systematics, which is quite complex to do this with limited resources in terms of computer. And so people are now making the plans to be sure that we get brand new results for the next spring and summer conferences.
Spring and summer, okay. We'll hold you on that. So we're looking forward to new results, 50 times more data than all up to now. This is a crazy increase. So we're really staying tuned for new results. And now let's see what was happening in the other LHC experiments. Let's go to Atlas in CMS. I think CMS is first, one of the 2 general purpose detectors that also has a heavy ion program. So let's go to CMS now.
All right, now we are at the CMS experiment, and today we have with us Molly Taylor, who coordinates part of Trigger for the heavy ion run for the CMS experiment. Hi, Molly.
Hi, thanks so much for having me here.
So Molly, since you're a Trigger coordinator, could you briefly explain us what is a trigger for an experiment like the CMS?
Yeah, sure. So I work on the trigger coordination, and what this does is it helps us choose which data we want to keep to analyze later. So you can think of the CMS experiment as a giant camera, where it's always watching what's happening inside of the detector. And we cannot record everything that happens. This is too much data. And so you can think of the trigger as like kind of glancing at the photo that would be taken and deciding, do we want to record this or not? And this year was particularly exciting because we implemented a lot of improvements to our trigger system. So we could actually record almost all of the head-on lead-lead interactions where the quark gluon plasma droplet is formed. And lead ions also do not always collide head-on and form the quark gluon plasma. Sometimes they sort of pass by each other and they interact very strongly electromagnetically. And these collisions are also very interesting because you can use them to study the nuclear structure. So we got orders of magnitude more collisions of these ultra-peripheral collisions than the previous years. And we got over 5 times more of the head-on collisions than in the past. So it's very exciting to analyze this data. It will be analyzed for many years into the future.
That's amazing. And how was this heavy ion run for you and the CMS experiment?
Yeah, for me, it was very exciting to be here at CERN. So I'm a PhD student, and due to the pandemic, I was not really able to come to CERN over the past year. So this is my first time spending a significant amount of time at CERN. And a huge portion of the CMS heavy ion community comes to CERN specifically for the heavy ion run. So we're all there to monitor the data taking, to do the quality checks and the performance checks, and to adjust and optimize the settings for our detector and for the trigger to get the best data possible. So it's super exciting for me to meet all of my colleagues in person, to work with people, to enjoy all the many snacks that you mentioned at the beginning. And yeah, it was a really great experience working on such a big and important project and getting to see all of the work come to fruition.
Yeah, the snack spot stuck with me because like I think CMS control room had its table full as compared to other experiments. I noticed that you're studying jet quenching in the quark gluon plasma, a PhD researcher from MIT. So could you explain us what is jet quenching?
Yeah, sure. So Sarah already explained the quark gluon plasma. And so what happens is you have the lead ions and they collide and they form this quark gluon plasma droplet. But this is ephemeral. It does not last long enough for us to shoot things at it, to scan it, or whatever to determine the structure. So to figure out how this liquid-like behavior is emerging, we have to use probes that are also formed in the initial collision. So sometimes when the lead ions collide, a quark or a gluon from the incoming nuclei will interact very strongly with a lot of energy transfer, and they fly off in different directions and form a spray of particles. They fragment into something called a jet. And when we have the quark gluon plasma, they will interact with it and lose energy and become modified in quantifiable ways. So this is what I study. It's called the jet quenching, the study of this modification and energy loss. In particular, I study a more specific kind, where instead of having two jets going off in opposite directions, you instead have a photon and a jet, which is a bit rarer, but it's a much cleaner process to study because the photon doesn't interact via the strong force. So it won't be modified by the quark-gluon plasma, and it can tag the initial energy and direction of the jet so that we can quantify much better the energy loss and if the jets are being deflected, many more interesting things to understand better how the energy loss and interactions are happening in the quark-gluon plasma. CMS in particular is outstanding at measuring the high PT photons and jets. So it's very good constraints for jet quenching.
Wow. Thanks a lot, Molly. And now it's time to move on to the other general purpose detector, the ATLAS experiment. Let's take a look.
So representing the ATLAS collaboration, I'd like to welcome Brian Cole, who's the former leader of the heavy ion particle analysis group, and now the leader of the ZDC subdetector. Hi, Brian.
Hi. Thank you very much, Peter.
So ZDC, I just said these three mysterious letters. What does that stand for? What is that?
Okay, so the three letters stand for 0 degree calorimeter. So these are devices that basically measure neutrons, mostly, particles that go straight ahead from the lead collisions. So this is interesting because when the lead nuclei collide, sometimes they don't completely overlap, and protons and neutrons that don't participate in the collision, they just go straight ahead. The protons get bent out by the beam magnets, so we never see them, but we can easily detect the neutrons, which basically go at 0 degrees from the beam. So by measuring these neutrons, we can actually determine event by event how much, let's say, overlap there was between the two nuclei, and we call this centrality. So that's very important for understanding the physics. Then we can do things like look at jets and jet quenching, right, for different classes of events, some that hit more head-on, some that hit less. The other thing...
Sorry, if you could just... Because we've mentioned centrality a couple of times already. So if you could just sort of, for our viewers, just sort of start to finish, talk about like what different centralities mean for the physics.
Sure.
Right?
So you can imagine you have, two nuclei colliding, and they can, basically just go past each other and either barely touch or maybe not even touch at all, and then they only interact through their electromagnetic fields, or they can hit head-on, right, or somewhere in between. And centrality is a way of describing whether they're hitting head-on, where you get the most particles out, thousands of particles come out of these collisions, or maybe where they're only grazing and you get many fewer particles, you also get less plasma.
Mm-hmm. So basically quark-gluon plasma appears in the most central collisions as
in
general,
principle,
right?
in all of them, but in the most central collisions, you get the most plasma, the hottest, it's also largest. So the larger the volume, the more sort of it acts like real material as opposed to individual particles.
Okay, but you mentioned also that sometimes the ions just pass by each other, but they still interact.
Yeah, okay, very good.
What do you mean by that?
So we call these ultraperipheral collisions. You can think of each nucleus at very high energies or velocity as actually a source of photons. And when the nuclei pass at large distances, a photon from one nucleus can scatter off the other. We call these photonuclear collisions. And in fact, my group, one of the things that we do is study photon-nucleus interactions, because you can actually study the quark content of the nucleus and its structure. Sometimes you also have collisions where both nuclei emit photons, and then you have photon-photon scattering. And this became quite interesting recently because the LHC was the first to observe the scattering between two photons into two more outgoing photons, what's called light-by-light scattering. This had been predicted, but it had actually never been observed with real photons until the experiments at the LHC.
But why did we need the LHC to? Because this only happens in the heavy ions. I never heard about the proton-proton collisions talking about light-by-light scattering.
So the photon-photon scattering does happen in proton-proton collisions, but the brightness of the photon beams is much higher with lead nuclei. So you gain tremendously from basically the large charge of the lead nucleus. It's also helps at the LHC because the very high velocity of the ions makes the photon flux extend out to much higher energies. So this could be done at other machines, but nowhere at the highest energy is at the LHC.
So there's much more to the heavy ion collisions than just quark-gluon plasma, is what you're saying.
Yes, there are.
Other
right.
phenomena.
And in fact, we're even using these photon-photon collisions to look for physics beyond the standard model, because in the photon-photon scattering, you might produce other particles called axions or other things that would indicate new physics beyond the standard model. We're actually also starting to contribute to that physics, not just in the proton-proton scattering.
So can we expect some axion results soon?
Well, we already have results from previous data taking, but with actually some of the upgrades that we made to our detector and to the 0-degree calorimeters, we're actually able to trigger better during this run. And so we actually expect to have new results on what we call light-by-light scattering and other measurements from this data set.
Fantastic. So another promise made. There's going to be a stream of results coming your way. But now let's turn our eyes to the LHCb experiment, which is a yet different type of detector that normally deals with CP violation, studying matter antimatter asymmetry. But it turns out that it also has a program of studying heavy ion collisions. So let's go to LHCb now.
So let's welcome our next guest, Elena De Loco from the LHCb experiment. Hi, Elena.
Hello.
How are you?
Good, thanks. Happy to be here.
Yeah, so Elena is the deputy run coordinator of the LHCb experiment. And Elena, we just walked through the CMS and Atlas sections, which are rather different from the LHCb experiment. The LHCb detector is known for its different geometry than most particle detectors. So how was this heavy ion run special for the LHCb experiment?
Yeah, so for us it was very exciting because it was the first time that we took lead data with the upgraded detector. So really, it's not just upgraded. We can basically consider it like a new detector because we completely changed the tracking system. We upgraded the particle identification system. And we completely changed our strategy on how we take the data. So right now, every time the LHC sends us a collision, we look at it and we decide if this is interesting for physics to keep it or not. So we do this every 25 nanoseconds. And for lead, this really means an improvement because it means that we can really look at more central collisions. So we discussed centrality just now. And we can now reach a higher centrality than what we could do in the past runs. So this is a big step for us.
Right. And yeah, how was this experiment for you? How was this run for you personally?
For me, yeah, it was really cool because it's the first time that I was overseeing the run as, let's say, run coordinator. So it was really fun to be in the control room, and I learned a lot about the ions as well. But also it was very special because for the whole run we injected actually gas. That's one of the things why LHCb is also different from the other experiment, and is where we can actually exploit our specific shape. So we are really developed in the forward direction, and this gives us an advantage when we can be a bit creative, let's say, with our detector. So we could actually inject gas and use it as a fixed target experiment.
How do you do that?
Yeah, so we use a system that is called SMOG, which stands for a system for measuring the overlap with gas. And it really means is what allows us to inject gas in the primary vacuum of the machine, which is where the beams pass through. So you can imagine that you have the gas that is at rest, and then the very energetic beam that is coming in. So you have the LED that interacts with the gas, and it generates a series of particles that are all in the forward direction, which is where our experiment lies. And that's why we can do these kind of things. So we can take measurements in parallel of the LED-LED collisions, like the other experiment, but simultaneously also take the measurement of the LED with the gas. And we can really inject different type of gases, one at a time, but we can inject, for example, helium, neon, and argon. So this year we injected argon for the whole time. But in the future, we will also be able to inject different ones. So for example, hydrogen or deuterium, or maybe gases that you're a bit more familiar with, like nitrogen and oxygen, that you can find in the atmosphere in big quantities. And this is important because then we can do a whole series of measurements that go closer to the astroparticle physics. Because, for example, we can really bring, basically in our experiment, in our lab, what happens in the atmosphere between the cosmic rays that come and interact with the nuclei in the atmosphere of the Earth. So that's why it's really cool to see this happening this year.
Indeed, that's super interesting, and that means you're looking forward to really exciting data with injection of these gases that's so LHCb specific.
Yeah.
And moving on, you gave a cue to our next section, actually. At CERN, we have several facilities, such as CHARM, where they're testing space electronic components against radiation, making use of these heavy ions. One such project is called HEARTS. So let's take a look. What is the HEARTS project and what do they do?
So the radiation that is present in space is so energetic that it basically passes through almost anything. So when you have an electronic component that is, say, driving your spacecraft or sending it from one point to the other, it's always impacted by radiation. Spaceflight is relying a lot more than before on commercial electronic components, and actually it's very advantageous to be testing these electronic components before embarking on spaceflight, and that's really why we need these heavy ion facilities on Earth, because we're able to test them in a laboratory environment, and it's these testing facilities that we are developing in the HEARTS project at CERN and in GSI. Part of the actual improvements would be to use detectors that are really tailored for measuring heavy ion beams. We're using these actually in cooperation with our colleagues from GSI, it's the other heavy ion facility in the HEARTS project. And actually what we're doing right now is testing if the detectors are showing us the same thing here at CERN as at GSI, so we can use the testing framework at both facilities.
So HEARTS. Our guest today is Ruben Garcia, project leader of the HEARTS project. So Ruben, thanks for being with us. So HEARTS is basically testing electronics to see how they would behave in space. So I was thinking that that's something that NASA or the European Space Agency would be doing for themselves. Why is something like this happening at CERN?
Yes, thanks Piotr for having me, and thanks for the question. So essentially, of course, the end users of the space applications are mostly space agencies, private companies now with the new space applications. However, in order to mimic the effects of radiation on electronic components and systems in space, one needs a large infrastructure, large accelerators, high energies, heavy particles. And this is why the access to accelerator infrastructure for electronics testing is essential to be able to validate the systems that actually are embarked in the satellites to ensure that they can work reliably in space.
So the ESA, the European Space Agency, sends you components and you test them for them, or how does this work?
So the way it works is that what agencies like ESA do, they define requirements, and these requirements are then picked up by the facilities, and what we would develop is a capacity in terms of beam and service to be able to enable those type of tests. But actually the users would be from ESA, or more typically from the companies and institutes that are working with ESA, with NASA, with JAXA, with the various space agencies and commercial companies that are now also starting to exploit, let's say, the usage of space. Yeah.
So you're here with us at the heavy ion table. So I was thinking, because like space, of course, there's radiation in space, right? So if you want to test electronics to see how they behave in a radiation environment, I would think you just, I don't know, put a radioactive source or put them next to a nuclear power plant or something. Do you specifically need heavy ions to do that?
Yes, so you mentioned two important sources of radiation, which are very relevant for what we call cumulative damage. So this is damage that accumulates over time. For instance, one could have a cobalt-60 source to do a gamma irradiation, or one could have a neutron reactor to do a displacement damage on electronics. But actually, what is very special about heavy ions is what we call the linear energy transfer. So it's how ionizing these ions can be. And essentially, test standards tell us that we need to perform qualification of components up to LET values that can only be attained with heavy ions. So things such as lead or other similar ions. So that's one of the requirements. The other one is to be energetic enough to actually be able to reach the sensitive parts of your component and system. So here really the key trade-off or the key sweet spot is the combination of how ionizing the ions are and how far they can reach in your electronic device or board or system.
So basically you take the heavy ion beam that is colliding in all these experiments from the LHC, just take it out somewhere and have it hit your electronics, or what is it that you're doing?
So actually what we do, instead of using the LHC beam, we use actually two steps previously in the accelerator chain. So we use the beam from the proton synchrotron. Now, the reason for this is, first of all, the availability of the beam and the availability of an experimental area suited for electronics, but also, even if it might not seem intuitive in the start, ions at higher energy have lower ionization capability or have a very flat ionization. So if you want the stopping power, the linear energy transfer is very constant with energy over many decades. And to actually have the LET increasing, you need to go to slightly lower energies. These are lower when compared to all the LHC experiments that we've been discussing, but they're still very high when compared to cyclotron facilities, for instance. So it's this area range, it's this energy range, sorry, that is what we try to exploit to get a good balance between being energetic enough to reach far in our components, but not energetic enough to be too low in ionization capacity, basically, and linear energy transfer.
Fascinating. Thanks for that. So, as you can see, heavy ions have very, very tangible practical applications for testing for space applications. But now let's turn to the Q&A section, right? So let's see what questions did we receive from the audience for everybody at this table. I think I have one for Elena, for LHCb. Which moments of the heavy ion run were your personal favorites?
Okay, let me think. Well, okay. For me, I mean, the whole run was very exciting because it was full of surprises. But if I have to pick a favorite, is when we did what we call the Van der Meer scan. So now it's a bit difficult to explain, but I try to do it because I'm working on luminosity, and the luminosity is basically you try to measure how many collisions happened in your system, and to do that, you need to have special measurements to calibrate your detectors to understand this, and you have a dedicated data taking where you do something special with the beams. So you offset the beams with respect to each other in different direction, and in this way, by taking data continuously, you manage to measure, to calibrate your detector and then measure your luminosity. And then at the end of the all data taken, we can say, oh, we collected this amount of collisions. And this is my personal favorite because it's a very stressful moment. You really hope that everything goes fine at the first go. And it's very fun to see the beams moving while you take the data.
So the answer to what was your favorite part is the Van der Meer scan.
Yeah, I would say so.
Fantastic, thanks.
All right, so I see another question from our follower called Mark E. Hammond. So thanks, Mark, for your question. And this question is for Roderick, who is an expert on lead ions. So Roderick, Mark is asking, why use lead rather than any other heavy element?
So this has to do with how well we can produce them in the source. I think after the source, say accelerating them through the various accelerators in the chain is not very different, but certain elements are easier to produce at the very start of the chain. It has to do with how, let's say, how we acquire these elements, and yeah, this is the ECR source. Yes.
All right, thanks a lot.
I see a question for Alice, so this is going to be for Sarah, by Sarah actually. Hi Sarah. Coincidence there. So what are some cool new things scientists are hoping to learn about quark gluon plasma now after this run?
Yes, so cool new things. So we are going to try to understand how charm quarks behaves with the quark gluon plasma. How they interact with matter, what is their... so what we want to do is to characterize, to do full tomography of the quark gluon plasma. And for this, as it was already explained, we need to understand how matter goes through this plasma, because we cannot observe it directly, we cannot produce it long enough, we cannot directly measure. So we have a lot of indirect measurement. And one of them is to look how all the charm particles go through and what is their path length and how they interact. So this is one super cool things we will look at. There are also a lot of very nice analyses which are trying to do many correlations. So not only looking at one single particle, but to look at correlation with other particles. Because one thing that came out after the first exploitation of LHC is that we see signs of QGP not only in ion collisions. We also see signs, measurements in proton lead and also in proton-proton collision in very high multiplicity events.
Hold on, there's like 3 quarks in one proton, 3. Yes. How do you make quark gluon plasma?
Exactly, that's the point. So for this, the thing is that even if there is only 3 quarks, you have a lot of C quarks, and in proton, for example, it's extremely rare, but you can produce, you can have collision which produce a similar number of charged particles than in peripheral lead, for example. And in those, if you do ion analysis in those proton collisions, a very small statistic sample, you see signs of things you don't understand or look like some collective effect. And so what we are now doing is a full program from proton-proton to lead-lead, and to do multiple correlation analysis to try to scan a bit everything, scan in multiplicity, scan in system size, to try to understand when the collectivity emerge in hadronic interaction. And this is a really cool thing.
So you're trying to see how many particles make a collective.
Yes, yes.
And also charm. That's really cool. Do we have other questions, Chetna?
I noticed some questions coming up, and maybe this one is for CMS, Molly. We have a question, and the person is asking, is this run more challenging than proton-proton collisions?
Yeah, so there's a lot of differences between the heavy ion run and the proton-proton runs. So one thing that's very different about heavy ion, which was mentioned by Brian, is that thousands of particles are produced in these collisions. So you're really saturating, very high occupancy in your detector. And so they're much bigger events. It takes longer to read out the detector. You have much more data that you have to record, so you're saturating your data acquisition system and recording as many gigabytes per second as you can. And so you have to adapt things for this environment.
Roderick, do you want to expand on this? How is it extra challenging with lead-ion collisions than protons?
Yeah, so as I already mentioned in the beginning, there are many beam physics processes happening in the accelerator with lead ions that we don't have with protons. I mentioned before the collisions and these one electron ions. Another point is that the beam has a very high stored energy. It is around 20 megajoule. So this is the same energy as a high-speed train cruising at around 55 kilometers per hour, but focused on a few hundred micron thickness, which goes down to about 15 microns in the collision point. And so if this beam would go in the wrong place, it can really make a lot of damage. So we have to control all the beam losses extremely well. To do this, we have something called collimators. And for ions, we use a special type of collimators called crystal collimators, which are basically 4 millimeter silicon crystals, which are bent. And then any ions that start to deviate from the wanted trajectory, they can get trapped in between the planes of this silicon crystal. And then they follow the bending, so they like bounce back and forth between the planes. They follow the bending, they come out with an angle, and then they hit like a big absorber downstream weather court. And to set everything up here and to align the angles, these crystals, etc., is extremely challenging.
Yeah, it sounds like a challenge you managed to overcome in this run. Like it was a short run, even though it was the longest heavy ion run, but you had to overcome many challenges in a short period of time. That's impressive. Okay, do we have some more questions?
Yeah, I have one for Ruben. It's actually mine. I wanted to ask this question. There's something else written here, but I have my own. But it's a very simple question. Hearts stands for what? Because your logo is like a little picture of the heart, but this has nothing to do with heart, right?
Yes, so basically HARTS is high energy accelerators for testing and shielding, basically. So that's the acronym. Of course, one needs to have a good acronym, and it's an EU-funded project, so it's funded by the European Commission, and it integrates CERN and GSI as infrastructure. So GSI is an accelerator in Germany that also has very advanced high energy heavy ion capabilities. And electronics irradiation is what we are mainly dealing with at CERN, but also at GSI. On top of the electronics, they also have studies for shielding, so to see how to optimize shielding against heavy ions, because these are a hazard also for human spaceflight, for instance, and also radiobiology, so how they interact with live tissue and what type of hazards it represents from the more health perspective in terms of radiation damage. And in addition to GSI and CERN, we also have industrial partners, Airbus and Thales Alenia Space, and we have an academic partner, which is the University of Padova. So these are representing the users. So they are the ones that have the end application and that set also the requirements and that help us, that guide us through the process of setting up the beam and the service, and that will ultimately validate this beam and this service to see if it complies with the real needs of end users, and that's the main purpose of the project.
So it's really broad.
Yeah.
Thanks. Do we have anything else?
I like a question, and perhaps it would be good to know from a machine point of view. Matteo is with us, who's an expert on the Large Hadron Collider machine. What will be next after this?
Okay, after this, we have just finished the run for this year. So we are going now into a period of maintenance where we stop the accelerator complex for the annual maintenance, and then we will restart in end of February, beginning of March next year. We will start with a proton run, and then we will have another ion run probably dedicated next year. So we'll have another exciting run in 2024.
I see there's a question about Atlas that we haven't. Well, we kind of touched on this, but somebody wants to know more, I guess, about ultra peripheral. What are ultra peripheral? I think we used this kind of buzzword, right?
Yeah,
maybe we didn't really.
Right. So the term ultra peripheral just means that the nuclei either just graze or maybe they pass by each other at very large distances. That's the peripheral. Ultra means that they pass very, very far apart. So it's only the electromagnetic fields that interact instead of the actual quarks and gluons interacting and creating a quark-gluon plasma. So those are collisions where, for example, one photon from one nucleus collides with the other, or photons from each nuclei collide with each other.
So this is really the photon scattering.
Yeah, it's a photon scattering, and that can happen at distances that are 10 times or even 20 times the radius of the nucleus. So they can be very far apart, and they can still interact.
They just wave at each other?
Yeah, they wave at each other, but in fact, one of the things that we see is that even when they wave each other, sometimes the nuclei just simply break up, and they also give us neutrons in the 0-degree calorimeter, and we study this as well.
Huh, that's pretty insane. All right, so as you can see, there's crazy things happening when these heavy ions even just sort of fly next to each other. I think that's all that we had in terms of questions. So thanks everybody for being with us. Thanks to you, our viewers, for tuning in. And this is the end of the heavy ion run from the CERN Control Center. Thank you very much.
Thank you.